All right, we are just about on time here. Welcome everyone. Thanks for joining for our webinar today. Today we're going to go over what's new in our Pipeflow products. We're going to talk about the key features in our new version showcase. So we have a lot of exciting things upcoming for our next round of versions for Fathom, Impulse, Aero, and Xstream. We're very excited to present some of these new things and get to hear your feedback and see how everyone is able to use these new features to make the most of the Pipeflow simulation software. This is not going to be a full consolidated list of every possible thing that we've changed in the new versions. For that, you'll have to check the release notes, but we are going to go over some of the major items and show some demonstrations how those things work and get a bit more information on that. If you have any questions, please submit them to the Q&A section. I will take those towards the end of the webinar. And if you have any technical difficulties, please submit those as well to the Q&A section. Our marketing team will assist and make sure that everything is working and functioning as needed. So without further ado, let's get going. My name is Simon Kitnick. I am an application support engineer with DataCore and Applied Flow Technology. I have been with the company for several years now on the support team, so I'm one of the first contacts you may talk to if you're reaching out to our support team for feedback, information, or anything like that. I'm now going to shut off my camera and get going into the software, make sure you guys can see as much as possible here. I want to start out by reminding everybody of the actual products that we offer. So our incompressible and steady state product, Fathom, models liquid flow in incompressible systems. Our counterpart, Aero, models compressible flow in a steady state instance. Impulse is used for transient behavior, fast transients such as valve slam in incompressible systems, and Xstream is a counterpart that models fast transients in compressible flow systems. We also have some additional modules, the extended time simulation, goal seek and control, settling slurries, and pulsation frequency analysis. There's several places where you can learn about the new features in the software. The first one will be the welcome window. So upon opening the software, once you've installed the latest versions, you will see a welcome window that'll list all of the major features with links directly to documentation pages and little blurb screenshots that talk about how to use those features and where to find them. So that can be a great resource when you're first getting used to the software to find some of that information. The documentation portal is a great resource for not only the new features, but all information related to the software. Our documentation portal is updated with detailed information about all of the features, and within the software, you'll find plenty of help links that bring you directly to our documentation. So that can be really useful just to read through how this feature works or just get a better understanding of what the feature really does. Lastly, from our support team, we're always here to help. You can reach out to us directly if you have any questions, and we can help provide any of that information you may need on new features, how to get the software set up, or any other related things to the software. So let's jump right into it with our first feature of the day, the Parametric Study. The Parametric Study tool enables rapid in-depth simulation analysis, which allows users to quickly explore how different combinations of inputs and parameters affect system performance in a brand new way. You can generate extensive scenario analysis with a bit less work trying to create all these individual scenarios and build out so much piping networks within the model. There's new tools that enhance the understanding of analysis and provide better system insight, and you can quickly identify trade-offs, sensitivities, and optimal conditions in your system with ease. So to showcase this, we're going to demonstrate this in Fathom here. This is a simple thermal study where we have an assigned flow junction providing a flow rate into a system. Our pipe, we are modeling convective heat transfer, and we have one layer of insulation here. And then we have an exit pressure of 500 psia. So this is delivering a high pressure fluid to a tank or some other system. What we can see right away is that at the top, we have this new parametric study section. So rather than just the simple run model, we can see that there's Parametric Study and some options here. I'll explain these a little more in depth in just a second, but first I want to open up the analysis setup and really showcase the how to set up a parametric study and where to find it. So first, in the analysis setup, there will be a new section for solution utilities where you can find the parametric study item. Here, you can specify independent and dependent variables to vary different parameters within the system and see how that affects your dependent variables. In this case, we created a thermal study here by selecting Run Selected Study and creating a new study. And we set up 3 independent variables. So we're going to vary our ambient velocity. This is going to be the velocity of the air outside of the pipe. We're going to vary the flow input, and we're going to vary the ambient temperature, again, outside of the pipe. When setting up these parameters, once you create your independent variable, you can give it a name, select the input you'd like to define, the specific parameter, and then which junction you're using. In the distribution section, you define how you want those values to be spread out. In this case, I'm starting at 10, going to 100 at an increment of 10. And you can see this shown here below shows the values that I'm going to be iterating over. Setting up a dependent variable, you don't have to specify this range because this is what we're solving for. Essentially, by doing this, we can vary different parameters in the system and we'll generate output for only the dependent variables that we specify. So rather than generating the full output window, we'll only generate information on the specific parameters so that this saves time running and saves time generating data. So once we've got our parametric study set up, from the main window here, at the top, we can select the parametric study from the dropdown, and then this gives us the ability to run the parametric. To run the model normally, you would just select the None option here for parametric study, and you can see this option changes back to Run Model. When we select our parametric study, it changes to Run Parametric. This is a quick shortcut here to access the parametric settings within the analysis setup, and this option opens the parametric data viewer. I'm not going to run the parametric study here since I've already generated data, but you'll see a similar solution progress window to when you actually run the model, and it'll go through the different iterations, and you'll see that reported in the information. Once that's complete, it'll give you the option to automatically open the parametric data viewer. Once the parametric data viewer is open, it looks like this, where you can see we have a ribbon at the top with several options. And if you had just run it, it would open up with the data automatically. Since I didn't just run it, I'm going to have to navigate to that file. So we'll go here and I'll open my thermal study parametric file. Now we can see that I've loaded the data. This is shown on the left, and the options have become visible, and now I can click on things. To showcase the parametric study capabilities, we're going to first start just by plotting a line graph. To start, we'll graph temperature versus flow input and click Generate Series. What you can see is this automatically creates a graph of this data, and so we can visualize how the temperature at the outlet of the pipe varies with different flows. As you can see, at low flow rates, the temperature is lower, whereas at high flow rates, it starts to even out. The parametric study allows for all of these parameters to be varied all at the same time and review different information through a mode of different methods. One thing to note about these line graphs is that we can actually select our other parameters here. So if I wanted to increase the ambient temperature, ambient velocity outside of the pipe, this will automatically update the graph. So we can see that if the ambient temperature were a bit higher outside, we can see how this starts to impact the graph at this state, where our flow input is still graphed on the x-axis and temperature on the y, but we can see how that ambient temperature outside of the pipe makes a difference on the shape of this graph. Now, this can be useful for graphing just one parameter crossed with another, but we can also create 2D graphs to show different demonstrations of these parameters. So next, we'll make a heat map of the ambient velocity and ambient temperature. By clicking heat map here, create new chart, and we'll select those options here and click Generate Series. First thing to note is that this does create a new tab at the top. So if you need to access previous graphs that you made, you can see those here. With this, we can now see a 2D space of this graph where we're graphing ambient velocity on the x-axis, ambient temperature on the y-axis, and we have our legend over on the right indicating that temperature outside at the outlet of the pipe. So as we can see, at low flow rate, at a low velocity and low temperatures, our temperature is going to be relatively low. But as we increase both our velocity and our temperature outside of the pipe, our outlet temperature at the pipe grows quite a bit. Again, we can drag our flow slider here to change what the flow rate currently is when we're looking at this. And we can see that at high flow rates, we actually notice that the ambient temperature and ambient velocity don't have a significant effect on the outlet pipe flow rate or outlet pipe temperature. And this is because if the flow is moving very fast, then it has less heat time to absorb heat transfer from the outside surroundings. Now, to show this another way, let's make a surface plot. For this, we'll do ambient velocity and ambient temperature again. And this gives us a 3D visualization of how these parameters vary with our system. Again, we can drag that flow slider to see how this moves, but as we can see, we're able to move around this 3D plot and really visualize in different ways how these parameters affect the temperature. In this case, we can see the same sort of representation as before, where when we're at a low ambient velocity and a low ambient temperature, we'll have the lowest outlet temperature in the pipe, and at high ambient velocities and high ambient temperatures, we'll have higher outlet temperatures there. If we were to change this to ambient temperature and flow, we can see how this updates the shape of the graph. And again, we can see that at low flows and low ambient temperature, we'll have the lowest outlet temperature of our pipe and the highest outlet temperature of our pipe at high ambient temperatures and low flow. We can see that at high flows, this begins to look pretty flat, indicating that at higher flows, this ambient temperature doesn't have a significant effect. For different ways to visualize this, we can also do this with scatter plots, which are a little easier to see. You can get a bit more transparency. Columns, which can show depth a bit more and show the shape, as you can see down here at the front. This is definitely the lowest and the highest points. I'm fond of the bubbles, where it's similar to a scatter plot, but at the larger values, these bubbles will just appear bigger. So there's a lot of different and unique ways that you can utilize the parametric study tool to generate a variety of different studies and vary lots of different parameters. We'll see the parametric study tool a bit later when we're showing in tandem with another feature. But ultimately, what's important to note is that the parametric study tool really has a lot of capabilities to vary a lot of different parameters in many different ways. It can be a really useful tool to help visualize data and save time creating lots of different scenarios just to vary maybe one or two parameters. I'm going to close out of this, and we are going to jump back to our slides here and move on to our next feature, which is the graph annotation tool. This adds an automatic updating graph directly into the workspace, which brings the functionality of the graph results window side by side with your model. It's fully resizable, movable, and easily hidden, and can help you create clear graphical diagrams and monitor key parameters with interactive and informative information on the workspace. To show this, we're going to switch over to Arrow. And we have a quick model here. This is one of our example models. And what I'm going to do is just run this model briefly, and then we'll return to the workspace and create a graph annotation. So this is a new toolbox item that you'll see on the left here, the graph annotation tool. This works similar to an annotation where we select the object, we'll drag out the size, and this will create our graph. We'll first make our compressor versus system graph, where we can easily see that the graph parameters, the graph list, are still here with the same functionality from the graph results window. We can click generate, and after a few seconds, we will see this populate a compressor versus system curve. Something else to note is that this graph tool does have both the options from the graph results manager or the graph results window, as well as annotation settings for customizing the formatting of the graph. Here we can see we've generated this graph directly on the workspace, and we can position this side by side with our system, making it easy to make diagrams and other things like that. If we need to change any of the content on the graph, there's a few options in the right-click menu where we can do some quick formatting options, change the scaling, or even copy the data from this. Otherwise, we can perform all of these actions from the annotation section here. Down at the bottom, let's say I wanted to make my title a bit simpler here. We'll change this to say compressor curve versus system. And you can see this automatically updates directly on the graph. There's lots of different customization options here, but a few things I want to highlight specifically is under the behavior option here. First, we have the show crosshair item. So when you enable this, when you're hovering over the graph, you will actually see the data points of the graph that you're showing. The highlight constituent objects behavior here makes it so that when you select the graph, the items on the model will get selected as well. To demonstrate this a bit better, we're going to load our static pressure profile here from our graph list, and you can see this updated automatically. You can also see that when I deselect and reselect this option here, it selects all the related pipes on the model that I'm graphing. If I were to turn this behavior off, deselect and reselect the graph, you can see that it no longer selects those pipes. Lastly is the replot after run. When we do this, normally the graph will update automatically when we're building out our model and when we're rerunning it. But sometimes if you have a larger model, this can take extra time to actually generate the graph and maybe make it force your software to load a bit slower. So it can be helpful to potentially turn this option off so you can only graph these things when you are ready to look at them. So in this case, I'm just going to rerun the model very quickly, and we'll go back to the workspace. And you can see that rather than automatically populating the graph, we're given this option to replot the graph. When I click this, it'll then generate the graph. And if you have a very large model or lots of different graphs that you're looking at, this can be helpful to save a bit of time. Make sure that your workspace is not loading all of these graphs and can make the process a bit more seamless. If you're curious about more information on how to use this tool or all of the options available here in the quick access panel, you can find this little help button down here under the annotation section. This will bring you directly to our documentation page where you can read about this tool and all of its capabilities. Moving on, we're going to talk a bit about the workspace layers improvements. There's been significant interface improvements to the workspace layers feature that was introduced in our last round of versions for the software. We've added folders for improved organization, quick layers for fast setup, and reintroduced the vary pipe thickness based on diameters. We've made it easier to navigate and customize your layers, added an advanced layers section, and you can also create scenario-specific annotations, which does exist beyond layers, but is involved with layers as well. So to demonstrate this, I'm going to jump back to Fathom, and I will open up a workspace layers demonstration model here. In this case, we just have a couple things set up just to showcase the behavior of the model. The Workspace Layers tab is located on the Quick Access panel, and you may see a few additional changes from the last versions. First, something that was introduced in the last cycle, but was really amplified recently, is the ability to save layers to file and to load layers from file. So this cooperates with the previous visual report feature, so you can actually load your visual report control directly into here, and now you're able to save your layers configuration as well, so you can have some standards I apologize. My headset just paused out on me there. So as I was saying, you can save the layers to the file, and you can load layers from file to make some standard set of layers that you may use in multiple model files or share among colleagues. The advanced layers section is now broken out to specify advanced layers directly in the layer section, making it a bit easier to organize. Folders can be made and controlled entirely from the visibility icons here. So as you can see, I have an output folder where I can actually toggle the visibility of all of these items at once. We've adjusted the all objects layer, so now there will always be one required layer in the model, but there's no longer an uneditable layer that there was previously. Within the UI of the layers window, we can see that there is a bit of change. First thing is that we want to note that previously there was a label control item. This has now been merged directly into the show, hide, and style section here, where we can see that the label control and object control are the same. So the label control relates to these actual labels for each object, whereas the object control will determine whether it's showing the object itself on this layer. You have the option to choose these individually or make sure that the object visibility and the label visibility align together. Something else to show real quick is the quick layers option, where you can quickly create new layers from output control settings or from workspace selections. So if I want to only do maybe the bottom half of this model here, I can create a quick layer from the workspace selections, give it a quick name, workspace, and see that these objects that I highlighted are the only ones that have visibility enabled. So this can be a quick way to populate your system or your layers. Doing another quick layer from the output control will automatically turn on all of the parameters used with output control. So now let's go ahead and show the vary pipe thickness option. When we enable this layer here, what you can see is that the pipes themselves have changed the pixel size. They've changed the size they visually represent based on the diameter of the pipes. This is configured by the vary pipe thickness option, where there's a choice to edit variance, which allows additional controls over how large or small those pipes get based on the diameters that the system is specified. With this option on, you can see that our larger pipes are 12 inches, are the largest visually on the workspace, are 10 inches somewhere in the middle, and our 6-inch pipes are much smaller. So this can be an easy way to visually represent your pipes in different ways. If you have varying diameters, you can see this directly on the workspace. Now I'm going to show some of those scenario-specific annotations. To do this, I'm going to turn on this annotation layer here, where we can see that on this scenario, all of these annotations are shown. If I switch to this scenario, the 1, 2, 3, only these 1, 2, and 3 annotations are shown, but I did not vary anything in layers. Similarly, with the ABC scenario, you can see only these annotations are shown, and again, we didn't vary anything in layers. This is customized from the annotation properties, which you can see down here at the bottom, where there's this option to select scenarios, and you can specify the specific scenarios that the annotation shows up in. With layers, this is configurable from the show/hide annotations, where you can also see the list of scenarios that an annotation is included in, and you can see its visibility in the current scenario. So you can toggle this and update these from layers. And while layers still controls the visibility of all of the animations together, you can specify only one layer that customizes these annotations and still specify them with specific scenarios to show up in. Lastly, I want to mention that there is a new layers toggle button up at the top. If maybe you have too much information going on your screen and you just need to reorganize, collect yourself, you can actually toggle layers, and this will turn the layers off and show full visibility of just the pipe tags, pipe IDs, or junction ID, pipe and junction IDs, and workspace symbols. You can see the workspace layers tab at the bottom has become grayed out as layers are disabled. So if you are trying to collect yourself, reorganize, or maybe layers is just not something you need to pursue right now and you need a more simple view of the model system without all these additional controls, you can disable layers through this toggle, and this will allow you to see the workspace in a more plain view. That's it for some of the workspace layers improvements, but we do have additional features that relate to layers related to the advanced sections. Our next feature here is going to be the design alert layer. This is a new layer that allows a new way to analyze your design alerts directly on the workspace, gives you the opportunity to quickly identify problematic areas in your model. It has an easy to configure interface and builds further on the layers and design alerts capabilities. So in this same model, I have some design alerts set up to reload a standard view preset I made, which just clears out some of this information. If I quickly show the design alerts here, I have a design alert for the flow rate in the upper branch, in the lower branch, and I guess I forgot to name this one, but this is a head loss through the heat exchangers. This may be because the heat exchangers, we don't want to damage any equipment. In the output, when we run this model, we can see that the design alerts do appear. We're not meeting some of these design alerts in one of the heat exchangers and in the pipe alerts in one of the paths. We can now visualize this directly on the workspace by creating a design alert layer. So I'm going to enable the visibility for this and show you what this looks like. Up at the top, we have some control options which allow different visibility of how the layer is displayed. In the center, we're able to select the design alerts we want to evaluate. And on the right, we'll see a list of the objects and if they have violated design alerts. We can quickly open the design alert manager from here as well to modify our design alerts as needed. So this is very simple to define. All you're doing is really selecting the design alerts you want to review. On the workspace, this color codes all the pipes and junctions to show which objects have no selected design alerts applied. These are in gray. A design alert applied but not violated, these are in green, and a design alert that is violated. We can see in the legend the design alerts that we are evaluating, and in the labels we'll be able to see what the design alert that is violated is. So we can see these pipes, the flow rates were violated and we're not meeting our minimum required flow rate, but this heat exchanger is fine. Down here, our pipes are fine, but our heat exchanger is not meeting the minimum required head loss, so we might be at risk of damaging this equipment. Any number of design alerts can be specified on these layers, and the colors can be customized from the global layers settings, which is the 2-gear icon here in the Workspace Layers tab. This can be useful for reviewing and visualizing problematic areas in your model and brings better visualization to our design alerts. We have another advanced layer here that we're going to talk about, which is the scenario comparison layer. This allows you to visualize scenario differences directly on the workspace, again, by color coding those differences and giving detailed inspection options to make it easy to spot modifications. To demonstrate this, we're going to open up another model here. Where we have a system of scenarios already set up, where this is a coolant delivery from a main supply to storage tanks. And what we want to evaluate is what would happen if we used 2 different pipe sizes, if we were delivering 2 different fluids, and if we were delivering them specifically to each tank. This is so in this model, we're reviewing all of this information. There's already some scenarios built out. And if we wanted to see the differences in these scenarios, previously we'd have to use the scenario comparison tool showing the information in a tabulated form. There it is, it was under tools. So normally we would see this information tabulated like this, but now we can actually see this directly on the workspace. So I'm going to create a scenario comparison layer. We'll just call this scenario comparison. And let's set up our definition here. What we can see in this layer settings window is that we have a comparison mode, specific and relative. Specific will manually select two scenarios to compare, whereas relative is going to compare scenarios based on their location in the model. So we're going to compare for this one, the current scenario with its next sibling. The additional settings here allow the definition of full scenario paths, whether the information is showed in the object labels, and whether we're showing any deleted objects if there are objects that are missing in one scenario but shown in another. We also have the option to view this comparison that we're currently doing directly in the scenario comparison tool so that we can see whether this in a tabulated form if we need to. For this demonstration, we're going to use the show full scenario path because we have some similarly labeled scenarios. And on the workspace, what we can see is our legend indicates we're comparing the 2-inch versus the 1.5-inch scenarios. And we can see objects that have no differences here are marked in gray, where objects with at least one difference are marked in pink. To see these differences, we can use the inspect window by holding right-click on the object. And we can see that in one column, it's showing the 2-inch scenario, another column is showing the 1.5-inch scenario, and we can see what these differences are. In this case, the pipe size has changed. If we were to compare a different scenario, such as the supply to tank A, since we set this up with relative comparison, we're still comparing it to our next sibling. So in this case, you can see in the legend, we're comparing the oxygen case supply tank A with the oxygen case supply tank B. So this changed both of our comparison settings. We can see that in this case, the pipes are the same diameter, but we have differences in the valves. When we hold our right click and look at the inspect window here, we see that in this scenario, we have no special condition applied to the valve, but in the supply to tank B scenario, we have the valve closed. And we'll see the opposite here, where we have the valve closed in supply to A and the valve open in supply to B. So this can be a great way to visualize lots of different scenarios, compare them at once. It can be an incredibly helpful tool for detailed inspection of scenarios, makes it easy to spot any modifications between scenarios, whether you're reviewing a model you haven't seen before, demonstrating a model for others, or just trying to review and understand the changes in your own model. This can be a great way to quickly review and visualize those scenario changes. Moving on. In the output, we've made some adjustments so you can quickly find maximums, minimums, sums, and means in the output. You can right click to automatically delete columns. This provides you with faster analysis right in the output window and we've given better selection functionality to the output window using shift click and right click to make different selections. For this, we're going to open up another new model, output control, and I believe I already have output here. What we can see in the quick access panel is there is now this selection tab. When we click on this, you can see that we see count, numeric count, max, min, sum, and mean. What we can do is start to select objects in our output, and you can see this populates information over here. By holding shift and clicking, I can select multiple objects at a time, and you can see that a max, minimum, sum, and mean is provided. This can make it really easy to quickly determine the total pressure loss or head rise, head loss between different components, and quickly select those through the output window here. By holding control click, we can also maintain our selection here and select individual objects so that we can pick and choose which ones we want to include in the selection. And now we can see that max, min, sum, and mean has been updated. We can also see the count for the number of objects I have selected, and it'll tell us which grid we're currently looking at. Additionally, we have the functionality to right click and remove columns now. Previously, you could only do this directly through the output control, but now you can just do this quickly right from here. If you have something maybe you don't need that is just not critical to the output, make things a bit easier, and this will remove it from your output control. So these features should make it a bit easier to utilize the output control to the best of its ability, display information that you're looking for, and make sure you can understand and interpret the output that you have. Moving on, we've added new heat exchanger models that allow for better calculations for overall heat transfer, for the overall heat transfer coefficient in heat exchangers. This accurately reflects how heat transfer performance changes with flow rate, and it's usable with any of the NTU effectiveness models. It provides a more realistic representation of the heat transfer process in the heat exchanger itself, and better captures geometry from different heat exchangers. In the heat exchanger properties window, you'll see a new option for overall heat transfer coefficient, where there are three new options: constant, which was the option available before, estimated, and vary with flow. When we do estimated, we have to supply the software with a conduction coefficient, K, and an effective conductive length, X. With a plate heat exchanger, this would essentially be the conduction coefficient of the material and the thickness of the plate. If you're using a different kind of heat exchanger, the following equation can be used to estimate that effective length. This can be seen just by holding that little tooltip, the blue dot here with the question mark, next to that, and this equation can be found. Additionally, we have this reference convection coefficient section where we have to specify some reference information to be used to determine a single data point to relate the heat exchanger convection to the flow. Reynolds number ratio exponent is going to be an estimated value, which ranges from about 0.4 to 0.8. The default will be 0.8. And by providing this one data point, we can estimate using the power law what the ratio or what the change in convection would be with respect to flow. With these new models, you can better capture the effects of varying flow rates through, oh, I apologize, and the vary with flow option. Forgot to mention this one. The vary with flow option allows you to directly specify the overall heat transfer coefficient with respect to flow rate, provides you a quick graph here, and if you have this information, it can be directly inputted into the heat exchanger junction. Now, these new heat exchanger models can better capture the effects of varying flow rates through the different heat exchanger geometries that you have to achieve more accurate heat transfer calculations. For another related feature to heat exchangers, we have finally added the ability to link heat transfer between heat exchangers between Fathom and Arrow. This has been a long asked for feature and it has finally made it into the software. This provides you with a more accurate and efficient workflow for modeling mixed fluid systems where you have a gas side and a liquid side. It helps to solve thermal balance in liquid gas heat exchangers automatically, and will save time performing manual iteration, copying information from Fathom to Arrow, and vice versa. So let's take a look at what this looks like. I have two models open here, where I have a Fathom model, liquid side, and we're going to open up our gas side here. These have already been set up, so we'll see this pop up that tells us that heat exchanger linking is on, and we want to allow this so that they can talk to each other. To enable heat exchanger linking, this is primarily done from the Fathom side, the liquid side. Under the analysis setup, in solution utilities, you'll find this thermal link option available when you have heat exchangers defined in your model and when you have heat transfer enabled. When you select the Run Thermal Links option, you will need to do this on both Fathom and Arrow in the analysis setup. You can see from the Fathom side, there will be this option to select the heat exchangers in the models you currently have open. In this case, we can see R3, heat exchanger A, B, and C in Fathom. And then similarly in Arrow, we can see heat exchanger A, B, and C. Sometimes this is something we're looking to fix, but sometimes that doesn't appear. So you can see these heat exchangers are available in the dropdown. This has already been set up, so I've defined my heat exchangers and which they're linking to between Fathom and Arrow. And what we can see is this will change our run option here to run thermal links instead of run model. When we do this, we'll get a new solution progress window pop up which is going to show the Fathom and Arrow converging at the same time, and we can see it jumps back between them. Once it says thermal link converged, we can select the output, and what we'll be able to see in both models here is that our information was transferred between the two and found convergence. To verify this, we should be able to see that the heat rate in should be equal and opposite between Fathom and Arrow. In this case, we can see that we have 965, 506, and 262 into the liquid side. On Arrow, we can see we have negative 965, negative 506, and negative 262 in the heat rate from into the gas side. When we specify it this way, the values that we put into the secondary fluid data here will be automatically brought in from the output. These will be initial guesses, so you will have to provide some information here in order to get the software started. But once you run the thermal links, these values will be varied to find convergence between both sides. So as you can see, we'll just enter generic 111 for each of these. This will clear our results. And if we run the thermal links again, what we should see is this is going to take a bit longer to converge than it did before. This is because it now has to iterate back and forth to find the correct answer. The closer your initial guess is, the quicker this may be. But you can see we did get thermal link iteration converged. And in the output, we'll see that we have the same results here, that 965, 506, and 262. And in Fathom, where we change these values to ones, we can go back and see that it will automatically populate this information. So that's how you can use thermal link between Fathom and Arrow to connect your heat exchangers between the two. I'm going to close out of these models here just to make it easier to showcase some others in a moment. Continuing on, we added a control valve sizing tool directly into Fathom and Arrow. And we also, I believe, we added global morph, which allows you to morph several junctions of one type into another, saves time, preventing tedious repetitive morphing. And the control valve sizing tool can automatically change your control valves to sized orifices and valves. I have another demonstration model here that will open up. Control valve sizing and global morph. This is one of our example files, and to demonstrate some of this behavior, we're going to make a couple child scenarios. First, we're going to global morph all of these branches to T's. To do this, you can find us in the Edit menu, Global Junction Morph, and it prompts you if you want to save before changing. And what you can see is you can select the junction type. For this, we're going to select branches, and you have the option to pick which ones you want to morph. In this case, we're going to do all. And we're going to change these to a T/Y and click OK. We get a pop-up that's just letting us know that this is going to disconnect some information from other scenarios if they exist. We can say yes, and we can see that all these branches automatically change to T's. We'll do auto rotate to make them look pretty. And any common data, so if we had a name, elevation, any design alerts or notes applied, this will be saved when we perform this global morph. Now, similarly to the way we did this with global morph, we can do this with control valves to automatically size them. So if I run this model real quick, we know that our control valves will automatically find the related CV, K factor, and equivalent orifice information for these valves. That's the purpose of these control valves, is to help size this information. From the Edit menu, we now have the option to morph control valves to either valves or orifices. In this case, if we do valves, we get the same, do you want to save this before? Go ahead and do that. And we can choose which control valves we'd like to morph. In this case, we'll do all of them. When we do this, you can see it automatically changes our control valves to valves. And when we open this up, we can see that it'll automatically input that CV it was found. So since control valves at a single steady state in time will be equivalent losses to valves or orifices with the same information, we can morph these control valves automatically since Fathom is a steady state solver. We do not have this functionality in Impulse and xStream because these are not steady state instances. When we morph these to orifices, what we would see is that they'd use the sharp-edged orifice, and they would use the orifice diameter parameter and bring that directly from the output as shown here in these parameters. These parameters for equivalent orifice area and diameter are not shown by default. As a reminder, you have to enable them from the output control. But both of these tools can be very useful in quickly changing a bunch of junctions to another type, or sizing control valves and changing them to orifices and valves so that you can quickly perform this process and make the workflow more seamless to change those junctions. Moving on to Impulse and xStream, we've added a feature where design alerts and events can halt transient runs. These new options allow you to stop the run when a transient condition is met or when a design alert is triggered, and provides you with more control over your runs. To demonstrate this, we'll switch over to Impulse, where we have a quick model here, and I will show how this is set up. In the simulation mode and duration panel, we can see that there's more options than there previously was. Before, we were only able to specify a start and stop time for our simulation, but now we see the option to end simulation based on event. There's no events defined in this model, so this appears gray, and end the simulation based on a design alert. In this case, I have a design alert for cavitation that just checks whether the cavitation margin is above 0. So this could be at the initial design phase when I'm building out a system. I'm trying to determine, okay, am I getting cavitation? I want to avoid this. So I'm just quickly checking and say, maybe this is a large model. I don't want this to run for too long. I want it to just stop if we see cavitation. By doing this, I've specified that when this design alert is triggered, it will stop the simulation. If it's not triggered, it'll run for a maximum time of 5 seconds. So if we start this run here, what we'll see is the simulation was ended because the design alert cavitation exists was hit, and it'll give us the time step. When we click OK, we'll see that partial results are available, and we can still review the results up to this point. We'll see under design alerts that it tells us when this design alert was triggered, and we'll also see an informational message in the warnings tab indicating that only the results before this time are displayed. This way you can quickly identify and stop transients if there's any events or design alerts that you don't want to see, which can save time in ensuring that you're not wasting time running a model and potentially obtaining results that aren't useful to you if these events occur. If you did want to continue running from this point, the transient transient control file is automatically made. From the analysis setup, we can do continue run from checkpoint, and we can see a checkpoint file exists where we can continue directly from where the simulation was stopped. This can be a super powerful tool, again, saving time, preventing unnecessary runs, and making sure that your system is stopping if it is going to run into something that you don't need to see. Now, our next major feature for Impulse is pipe filling and draining. We can now model the propagation of one or more liquid gas interfaces throughout a pipe network. Draining, flow splitting, and compressible pockets of fluid can now be modeled, which can help initialize systems as dry or fill them, implement liquid staging, or analyze surge initiated by gas movement. To demonstrate this, we have another model here. This is a quick spray discharge system where we're supplying the system with fluid, but it is initially gas full. To define this, under the analysis setup in transient control and transient cavitation, we have to select this option for enable filling and draining. By doing this, we're explicitly telling the solver not to model cavitation. It'll be clear as we take a look at the pipe properties window, but what we are modeling is the gas and liquid as individual interfaces and tracking their movement throughout the system. As a result, this feature is intended to model filling and draining and gas bubble movement. This is not a two-phase solver and does not model mixed fluid flow. The gas is treated as a bulk fluid volume, and compressible calculations are applied individually to this volume throughout the system. So let's take a look at a pipe and see how this is specified in the workspace. When this is enabled, we'll see a new filling and draining tab. where we can specify whether the pipe is liquid full, gas full, or has some kind of interface. We can see a representation here where we'll see the upstream, downstream junctions, and we can see where that liquid line is defined. If we were to update this percentage, we can see this update directly on the diagram to give a bit of a view of what this would actually look like. Now, I've already run this model, but what's important is how we can visualize this information as the pipes are filling and draining. The one way to do this is through the output. We've added new parameters into the pipe transient section, specifically for the gas volume or gas volume as a percent, and liquid volume as a percent. However, tabbing through tons of data is not the easiest way to do this. What we can do instead is create graphs and animations. What I can show here first is this pipe 5 inlet gas volume versus time. This is a transient pipe graph where we can see that at time 0, this is completely full with gas at about 200 feet cubed, and somewhere between 0.00 and 0.01, we get a steep drop in the gas volume, and now we are liquid full. This is because this is only a 10-foot pipe, so there's not a ton of volume to show. If we instead look at an animation here, where this is just going to be a path from our inlet to one of the spray discharges, we have the option to animate this, and we can see how this, we'll speed this up just a little bit, and we can see how the gas moves in the system. So in this case, we're slowly filling the pipe with fluid, the gas is slowly leaving, and we can see how this trends as and view how much time it takes to perform this. Another way we can represent this is directly on the workspace through the use of animations. I've already set up a pipe filling animation here, where what we can see is I'm comparing the percent of gas in the system. We can see our interface is defined here. And when we play this animation, which I'll need to speed up a bit, we can see how the system is filling with liquid, how fast it's doing this, where the liquid is going, and see how that disperses through the system. Since all of these pipes are defined equally, same losses, same lengths, we see that this is about an equivalent spread of liquid. But if in a more complex system where there's different lengths of pipe and different things like that, this can be really useful to determine how fast the system is filling or draining. So that's how you can set up, model, and review a liquid and gas system where the gas movement is. You can see gas volume and how the system is being filled or drained. Our next item for Impulse is automatic and improved sectioning. We added a streamline sectioning panel, which improves modeling workflow and user configuration. This includes some new options to specify fixed minimum number of sections or a fixed time step. And the sectioning is now done automatically, no longer requires user input. What this looks like in the software is the pipe sectioning panel has been a bit reframed. We've previously moved some of the information that was under advanced settings out to the front, so the maximum allowable absolute variance can now be defined directly here. The sectioning mode has 3 options: automatic, which was done before but has been improved so that this is now no longer requires user verification. This will automatically find the minimum control section count. So whatever the minimum amount of controls, minimum amount of sections in the controlling pipe under the absolute variance tolerance, it will be selected. You can choose to specify a fixed section count in your controlling pipe, or you can choose to specify a fixed time step, which can allow much more advanced control over the sectioning in your model. Specific pipe information is still shown below, and some information is shown to the right, explaining the information about the option, the sectioning mode that you select. This will make sectioning a bit quicker and a bit more seamless, allowing you to build out your system better and making the sectioning process much faster. Our next item for Impulse is the improved reciprocating pump. where we've added advanced reciprocating pump options to provide better accuracy and definition for positive displacement pumps. In the pump properties window, you will see that when you select positive displacement pump, there's now an option for reciprocating pump. You can specify the pump as single acting or double acting. The cylindrical arrangement of the pump can be chosen, and there's several different options available that'll affect the shape of the flow versus time curve for each motion of the pump. The number of cylinders, operating speed, bore, stroke, and rod length can be defined the same as they could before, but now more front and center and easier to see. The rod diameter is used specifically for double acting pumps. You can now also specify an initial crankshaft phase shift to provide initial condition for the pump. This is an optional input. And you can also specify valve timing controls to capture more detailed effects from your pump's geometry. Alternatively, this can be estimated by entering the pressure rise and percent clearance for the pump. As you enter all this data, the plot for the flow versus time for one period will update automatically, providing you with a visual representation of the periodic motion for the reciprocating pump. With this new control, positive displacement reciprocating pumps can be modeled with much more accuracy and control. I apologize if we're moving a bit fast, just trying to make sure we get through all this information on time here. Our next feature for Impulse and xStream is the Pulsation Frequency Analysis workflow improvements. This is specifically for the Pulsation Frequency Analysis, or PFA, module, which is an add-on for Impulse and xStream. This is particularly important, especially with reciprocating pumps, when it's important to consider excitation frequencies and pulsation effects on the system. The Pulsation Frequency Analysis group has been consolidated into a single item in the analysis setup. The user interface has been adjusted to make it easier to create pulsation studies, as well as minimize some of the requirements to better suit individual user needs. Here we can see that we can still perform natural frequency analysis applied at one of our assigned flow junctions as we would do before, but the input information that we can supply has changed just a little bit. This is being harmonized with xStream, where some of this information was already included in the software, but now Impulse and xStream are performing the same behavior with the same interface, and it's been improved just a bit. Now we can toggle the option to model excitation RPM scenarios if sufficient information isn't available. This was forced before, but now it's optional. This will allow us to still generate frequency plots and review excitation frequencies, but we will not be able to automatically generate scenarios for evaluating the pump at those RPMs if we don't supply this information. If instead we want to perform a steady state pulsation analysis on a pump that's consistently operating at a specific RPM, we can now do so directly. We can now do so quickly using the steady state pulsation option. Here, we can select a reciprocating pump from the model to use and run a pulsation study at the pump operating speed. This way, the pumps can quickly be evaluated against API 674. Something that is important to show here is that if we open up another model file here, this is a quick pulsation analysis of pump J11 in a spray discharge system. We can create a parametric study specifically for evaluating our pump against API 674. So what I did here is we have a pump RPM as our independent variable, where we're varying the operating speed of our pump at junction 11. And our dependent variable under global results is this max percent above API limit. Now this takes a bit to load, so I'm just going to open the parametric data viewer directly and open up a saved parametric file that I have available. And what we can see is we can quickly analyze our pump operating at a variety of different speeds and evaluate whether they're violating this standard. So we can see here, we zoom in so we can see 100. Our lower RPMs are within our tolerance, but we have a pretty significant spike somewhere between 170 and 190 here. In this case, we can quickly identify that this would be an unsafe operating condition for our system. But further down, we can see again that we start to dip back below 100% of our API limit here at higher RPMs. So this can be a quick way to perform a speed sweep and check the operating conditions of the pump, and we can quickly evaluate our pumps against API 674. This is another great way we can utilize the parametric study tool to perform a quick analysis on pump speeds and evaluate these against different standards. Now, as we move on to our next feature here, I want to note that we are just at about time. We just have a couple more slides to go, so if you can stick around for just a few more minutes, excellent. If you have to jump off, this webinar will be recorded and posted to our YouTube channel some point in the future, so be sure to check that out if you do have to drop off. Our next feature here returns back to all of the software and is our improved PCF export. With this, we have better control over importing model files from the PCF file format, where we now allow for multiple PCF files to be imported at once. We've updated our file selection method. So if you've done this previously, we used to have to select a folder. It was a bit clunky to do. We can now just search for files directly and put them directly into the software, which makes a much more seamless transition using Windows File Explorer in order to find those files. We've improved the import for valves by adding the capability to read valve types for standard valves, check valves, relief valves, and pressure reducing valves. We've added improved import for concentric reducers, so we've added better conversion to our area change junction. And we've also improved the import for welded components, which will now import these as junctions with zero length connectors, connecting them to represent two welded junctions together. We've added the ability to globally change length units of pipes on import. So under the options section, when you're in the PCF import wizard, we have this section here where we can see there's a drop down for pipe length units and pipe diameter units. These were previously only set by the PCF file itself and could not be changed within the software here when importing, but now we have the ability to automatically change that, and it will adjust those units and bring those directly into your pipes, making, again, a bit more of a seamless import process. We've added the functionality to specify wall thickness and outer diameter for nominal sizes, simplifying pipe material conversion from imported files. When we select the edit pipe specs option, we get this new window where we have a drop down for the piping specification as imported from the information available in the PCF file. Since this does not translate well to our software, we have added the option for you to quickly specify each of these nominal sizes, what those outer diameter and wall thicknesses are. By doing this, this is essentially globally specifying this nominal size means this outer diameter and wall thickness. By doing this, this will apply it to all of the pipes in your imported model, and this is sufficient information to fully define the pipes in Fathom and Arrow. So this can make a much quicker process defining this information rather than having to go into each pipe and adjust the sizes as necessary. Lastly, we added the functionality to flip upstream and downstream junctions upon import. Clicking the Edit Pipe Connections will open up this new window where you can specify the upstream downstream junctions to help fine-tune some of the information when you're bringing in a model. All of this is done upon import, so you can set all of this information up as you're trying to bring that model from PCF into the AFT software, and that can make it much quicker to make these adjustments so that you can get started right away modeling your pipe flow system with our software. Lastly, we have some additional features here that I want to mention. These do not have demonstrations, but can be viewed online in our help site, as always. We've added read-only and password-protected models. So this is from the edit menu. You can now add passwords to your models. So only users who have that password can access a model file, or allow read-only to, if guests, to use the model in a read-only mode. So changes aren't made except by allowed users. We've added a new HDPE piping material library from ASTM F714. This is just to expand our piping material library and include more pipe materials from known standards. We've added the functionality to export a list of all pipe junctions with IDs. This can be particularly helpful when you're performing Excel export, so you can relate specific junctions, their IDs, to any sort of export of information that you do. This is also found under the edit menu. I apologize, under the file menu. Same with the password, under the file menu. Uh, in these latest versions, we have significantly improved the workspace handling for large models. So users who have very large models, we're talking thousands of pipes and junctions, previously may have experienced some slow loading times, or the workspace was difficult to use. We've significantly improved some of the handling in the backend for these models so that the workspace and usability of the software is more efficient, more effective, more seamless. We've extended junction parameter consistency checks, which means when you are specifying a junction, we've added more checks to verify that the information you entered is valid and ensure that more information is provided to you so that you can understand when you see a pop-up, here's why you're getting this pop-up, here's what still needs to be defined, here's what might be wrong. We've added the ability to save libraries into custom locations other than the local user library. So when you're creating custom libraries, you can now have better control over where those live and how they're accessed. Some specific features for Aero and xStream. We have added additional compressible flow modeling parameters into the output and all other forms of reviewing output information from the ANSI/ISA 75.0101 standard. We've added new loss models for inline flow coefficients in orifice and venturi junctions. We found that these are more accurate loss models and made these updates to make sure that when you're modeling orifices and venturis, it's using the most accurate method possible. Some specific changes for impulse. The first row of transient data is now initialized with steady values. This is actually available in xStream and the XTS modules as well. But essentially what this means is when you're defining a transient behavior in a pump or in a valve, the steady state has to match the initialization at time 0. Previously, you had to specify this manually, where you had to input that, oh, the CV of a valve at time 0 also matches what I specified in the loss model section. This is now done automatically. So when you specify your information at steady state, this will be automatically filled in at time 0. Modified wave speed has also been added to the output for impulse so that you can review the modified wave speed in each of the pipes. And in the settling slurry, the SSL module, slurry parameters have been added to the color map layer for better demonstration of different slurry parameters and making sure you can visualize that in all of the new ways that we've added and expanded with workspace layers. Thank you all for joining. If you're still with us, be sure to check out our other webinars and content online. Be sure to utilize our documentation portal for any assistance with new features and any other pipe flow software information you're looking for. When you're in the software, you can find these help buttons all over the place in every property window and on every menu. So it should be easy to open up our documentation and locate the information you're looking for. Otherwise, our support team is here to help. You can always contact us with any questions or feedback, and we'll be sure to guide you, help you out, provide you the right resources you're looking for. So once again, thank you all for joining. I'm glad you could tune in for our new features webinar. I hope you enjoyed, and I hope you're as excited as we are on the AFT team for all of the new features and changes to come with the next versions of our software. Thanks again.